In the last lecture, I proposed that if we want to characterize the running time of an algorithm analytically, so if we want to come up with some expression for the algorithm of its running time in terms of the input size n, so for example, if I want to be able to say t of n equals 3n plus 3, where this is the number of operations needed to execute the algorithm on an input of size n, I propose that one way we could do that is to invent our own hypothetical architecture and then count how many operations the algorithm requires on that architecture. The reason why I said that was a good idea is that if we want to count operations on a real architecture, on some real processor that exists, that can be really unpleasant because processors' instruction sets aren't designed to make that convenient. They're designed to run quickly and to actually do computations. If we invent our own hypothetical architecture, then the counting process becomes easier. It becomes something we actually are likely to be able to do. That was a big leap because, of course, if I want to solve a problem and I say, well, hey, I'm going to invent my own fantasy world where this problem is easy and then solve it there, you should be sort of skeptical about that. Who says that the solution that I come up with in my fantasy world where the problem is easy to solve actually maps on to any real case, any case that could occur in practice? So I have some ways to go to justify that. What I intend to do is to show that even if on my hypothetical architecture the algorithm can be analyzed to take, let's say, 3n plus 3 operations, and suppose it's the case that on the processor I have in my laptop, the algorithm might end up taking 100 times n plus 200 operations. And on the processor in my phone, it might take 159 times n plus 78 operations. What we'll see today is that for the sake of comparing algorithms together in a broad sense, we don't actually care that much about constants. We care about the rate of growth because we care about how the algorithm performs as the inputs become larger and larger. And that means that all three of these basically grow proportionally to n. And because of that, because I don't care that much about the minutiae of all the constants that are involved, it doesn't actually make that much of a difference that I used my hypothetical architecture. It's true that I have to justify that my hypothetical architecture is similar enough to a real architecture, that is, it supports the same operations and that I'm counting those operations, that the up to a constant factor, my analysis is correct. But I think that you'd agree if you take a look at the operations we defined last time that those do cover all of the operations you would need to run a typical algorithm on a processor like the ones we have today. And that means that if I'm performing analysis that only cares about the rate of growth in terms of n, and it truly can ignore all of the constants, then it is actually fine to use my hypothetical architecture instead of a real one. So the purpose of this lecture is to try and drive home that point, to try and justify a bunch of the claims that I made last time, and I think we'll have it done by the end of this lecture. I will come back to it in one future lecture when we talk about recursion. What we want going forward is the ability to glance at algorithms and perform analysis that is relatively convenient for us, but still rigorous, and doesn't require us to do something so tedious that it's likely to have a very high chance of error. So even with our hypothetical architecture from the last lecture, we have to be very careful because if we miscount, so for example, if I get 3n plus 3, but the real answer is supposed to be 3n plus 4, that could be a bit dangerous. And we're going to show that it turns out we don't need to worry about that. If we truly can ignore constants, then all we really care about is that we get something that's basically equal to n here, or that grows proportionally to n. We don't care that much if it's 3n or 5n or 3n plus 7 versus 3n plus 8. So our goal is to find a straightforward way to compare two algorithms based on their running time. Now, in this case, when we talk about their running time, we mean an analytical expression of their running time. So, for example, a function like f1 of n equals 3n plus 3, or f1 of n equals 3n squared plus 2n minus 7, or whatever. So some expression in terms of the input size n that describes the running time. And as I mentioned last time, in this course, we're just always going to use n as a shorthand for input size. So often I don't even say the input size n, I just talk about n. And generally speaking, when we parameterize an algorithm's running time, we do so based on factors related to the input, which is usually the input size, although not always. Later in the course, we'll notice that there are cases where we can characterize the running time of an algorithm based not only on the input size, but certain properties of the input. And in some cases, that's something we do in general, so that's the only analysis we perform, and in some cases, that's a separate analysis that we perform because we still want analysis just in terms of the input size. So last time we developed a technique that lets us characterize the running time of an algorithm based on the input size by counting operations on the hypothetical architecture that I was just talking about. We still need some way, though. If I have two different running time expressions, so suppose I have f1 of n equals 3n squared plus 2n plus 7, and then I've got f2 of n equals 17n plus 2n log n base 2 of n plus something really bizarre like 1 over n. That's weird. If I have these two expressions, the question is still which algorithm is faster. I mean, if one algorithm has this running time and one algorithm has this running time, which algorithm is faster? I want some way of comparing them, and we're going to see in a minute that we have ways of performing comparisons mathematically. So one example is a less than operator, but they're not going to work for this. We need something a little bit more general than that. And we want something that's relatively easy. So whether we can perform analysis on a hypothetical architecture or not, whether that's a good idea or not, there's still a question of whether it's something that's worthwhile, even if it's rigorous to do so, even if it's valid, if it takes forever, because the algorithms we analyzed last time took several minutes to analyze, and it was pretty tedious and error-prone, and we're going to work with much more complicated algorithms than that. We need to have a workflow, a process for analysis that is somewhat convenient to us, that we can do relatively easily. That doesn't mean that it's an easy problem, but something that we can perform with I guess, a reasonably high chance of success, and something that we can still verify as rigorous for our purposes. All right, so suppose that we've designed two different algorithms. I suppose two algorithms for the same problem, and they have these two running times. And I want to compare the two of them. And I should observe that if you had to analyze algorithms counting operations one by one like we did last time, then take pity on the poor person who had to analyze this. I mean, imagine what you would have had to do to come up with this operation count. It would have been pretty unpleasant. And then same story here. So, of course, we can already see examples where there could be algorithms with these two running times. We would rather not derive these by counting them one by one. We want the flexibility to, I don't know, ballpark it and not just say plus 100, but, plus some constant c. Or we want the flexibility to allow for a certain insulation against minor errors. Like if I don't count 100, but I count like 95 here, I hope that's not the end of the world, because otherwise it's going to be very difficult to make sure that I'm doing my analysis correctly. So I want to compare these two algorithms and decide which one is faster. So, of course, what I sort of want to say is that one function is less than the other, so f1 is less than or equal to f2, or vice versa. We're going to see pretty quickly that we can't do that. So here's f1 and f2. I'm going to apologize in advance because this lecture is full of plots that have lots and lots of functions on them, and they become quite cluttered, to the point that I've actually had to avoid using dotted lines in some cases because they make the diagram even more cluttered. We'll see only a few dotted lines. What we can see, though, is that if we try and use the less than or equal to operator, so I can't make the statement that f1 of n is always less than or equal to f2 of n, or vice versa, because although it's the case that down here, when n equals 1, it is true that f1 is less than f2, they trade places. So somewhere around, where is that, like 6 or 7 or something? After 6 or 7, it appears on this plot that f1 is suddenly taking longer. So f2 is now coming in with fewer operations. So of course, I can't use the less than or equal to sign, because to say that one function is less than or equal to another is to say that it's true always for all values of n. Or of course, I guess I could say something like f1 of 2 is less than or equal to f2 of 2, but that's not worth anything to me because first off, 2 is not a very big input size, and of course, I want to talk about arbitrarily large input sizes. And I also will observe that although what we're doing today with these visualizations, with these plots that we're currently looking at, is plotting analytical expressions of functions, it's not the same as performing an experiment. Reading the data on these plots comes with all of the same risks as reading the data from an experiment. That is, if I perform a timing experiment, and I don't know the functions yet, I perform a timing experiment and I see these two lines, of course I should be very wary about saying, oh, the red line is on top, that means this algorithm is always going to be slower. Obviously, we can't make that assumption. We can't generalize anything from just looking at the data on a plot. So here I'm plotting on very small values of n, so inputs up to size 25, which we already know. We probably don't care about that. We don't care that much which algorithm is faster on n equals 25. We can see that in this very local view, it does appear to be the case that the red line is taking longer, and the blue line, so F2, is taking fewer operations, but we should know by now that that doesn't really mean anything to us. So if we zoom out a bit, and we take a look as the input size increases to, in this case, 100, which is, again, a very, very small number in the grand scheme of things. Well, maybe you expected this to happen, but sure enough, it turns out that they trade places again. So if we had myopically decided, based on looking at our previous plot, which goes up to 25, that the red line is going to take longer, well, you know, it turns out that hypothesis was incorrect. Although, of course, we can't make any assumptions based on this plot either. The functions traded places. Who's to say they don't trade places again? What we care about is, as I drive n to extremely large values, I think it's reasonable to expect that they're only going to trade, these two functions are only going to trade places a finite number of times. Eventually, one function will come in, will take off and be larger than the other forever, after a certain point. And I want to emphasize that logic early because it turns out that later, the technique we end up using relies on that definition. That if we want to talk about which function's less than the other, we're going to come up with some point way off to the right where after that point, one function is always greater than the other, or always greater than or equal to the other. So in this case, we notice that F2 now appears to be taking longer than F1, even though we're still looking at very small input sizes. And if I zoom out further, so I've switched to a logarithmic plot here, just like I did last time, because I intend to zoom out quite a ways. We notice that it does look as if, although we should be very careful not to generalize from this, it does look as if F2 has held its lead for the time being. So apparently up to inputs of size 10 to the 5, 10 to the 5 is not a big number, we have F1 taking less time. But then I zoom out further and, you know, you should have seen this one coming, but sure enough, it turns out that F1 ends up taking longer again. So this, we could do this all day, right? I can design functions, and I mean, I'd like to believe that I've been quite civilized here. I've designed two very realistic looking functions that could actually be running times. We could come up with, if I'm allowed to use any functions that I can think of, I could come up with functions that trade places over and over again in the most weird, mysterious, random way possible. So you never see it coming, but they keep trading places. So hopefully this is enough to justify why we can't really pin down and say, okay, well, we're going to look up to this input size, or we're going to look up to this input size, 10 to the 10. 10 to the 10 is a respectably large number, because we don't know whether they're going to keep trading places forever. And of course, it's true that there are cases where you do only care about inputs of a specific size. But this is not one of them. The study of algorithms in a general sense is not one of those cases. We care about arbitrarily large input sizes and the behavior of algorithms in a sense as n goes to infinity. So at large enough scales, what we can observe, so this is actually, if I look at the plot we have on this slide here, I'm actually at the same scale if I go to the next slide. It jumps a bit because I'm adding a couple of extra lines to it, but we're still going up to 10 to the 10. And what I've plotted on this slide is I've also added two extra functions, G2 and G1. They're in the wrong order there, but they're both there. And each one of them, so G2 and G1, corresponds to the highest order term of each of the two functions. So yeah, I apologize about the mislabeling of G2 and G1 and G2 there. They should be labeled in that order. So you can see that the dominant term, I claim at least, in F1 is this term involving n cubed. And the dominant term in F2, again, according to me, is this term involving n squared. And I've plotted those by themselves, so the green line and the purple line. And what you'll notice is, even at this scale, so 10 to the 10 is, as I said, a respectably large number, but it's not as massive as some of the numbers we saw last time. Even at this scale, notice how the dotted green line, that would be G1, the n cubed term, the dotted green line and the line for F1 end up basically looking identical. They blend together. Whereas here, the line for F2 and the dotted purple line settle in and also look identical, even though the dotted green line and the dotted purple line only encapsulate some of the information, some of the terms of F1 and F2. And eventually, so if I keep zooming out, if I go to 10 to the 100, now that's a healthy size of number right there. I think we can call that a big number. Although we could always, talk about this number too if we're worried that 10 to the 100 isn't quite doing it for us. If we zoom way out as we did at the end of the last lecture, we can observe that basically they become indistinguishable. So if I look at this 1 over 10 to the 7 n cubed and 1/2 of n squared, at this, when I've zoomed out this far, at this resolution, they look identical to the function from which they came. So f1, if I look at f1, it turns out that this 5n doesn't really make that much of a difference at this scale. And this 3n log n, still not much of a difference. And in f2, the negative 5n, I mean, it has an effect, but I can't see it at this scale. And I certainly can't see the plus 100. So all of the functions, as I keep zooming out, as n gets larger and larger, their highest order term dominates the expression, and it basically takes over. The function eventually begins to behave basically just like its largest order term. And the slide is now pointing out the obvious, which is that their lines basically appear identical. If I hadn't used dotted lines, it wouldn't be clear that we even had 4 functions on this plot. Now, formally, this is a relationship. We can describe this as, we can say f1 asymptotically approaches 1 over 10 to the 7 n cubed. So that would be the line corresponding to its highest order term. It asymptotically approaches that. And you're familiar with what an asymptote is. And it's sort of, we can think of it like that. Basically what's happening is as I keep zooming out, I notice that the two curves approach each other, or that I actually like to think of it like f1 is approaching the curve for 1 over 10 to the 7 n cubed. And I guess I should say similarly, we can say that that f2 asymptotically approaches 1/2 of n squared. So each of the two functions asymptotically approach their highest order term. One thing, I want to put a bookmark here for something else, which is that, so this is neat, and actually one algebraic observation that we can all make from this is, if I look at a function that's a bunch of different terms like this, this is not a polynomial per se, but a function that's got a bunch of polynomial-like terms, that log n sort of gets in the way of that. But if I look at a function like this, and it's clear to me that one term is larger than the others, that is, I can sort of recognize that n times log n is, well, okay, here's my logic. N times log n, okay, we know that log n is less than n. Log n grows more slowly than n. I'm saying this very informally. Then we could say, I'm going to put this in quotes, we can say n times log n is less than or equal to n squared. Okay, and then n squared is obviously less than or equal to n cubed for positive numbers. And that means that it's reasonable to say, well, this is probably the highest order term. So you could glance at a function and look at it and say, well, clearly this one of these terms is the highest order one, and therefore I should ignore the lowest order ones, and I can think of this as being the key, the thing that's responsible for the rate of growth of the function. And the same thing is true of f2. I can stare at this and say, okay, well, that's obviously the highest order term. I'll ignore these two. That is sort of where we're going. However, we're sort of lucky here. We have these functions that are a bunch of different terms where the terms look sort of civilized. I mean, they look like something we've seen before. They're something that we're used to. We know what log n is. We know what n squared looks like. So we can stare at it and just figure out what the highest order term is. That's a luxury we don't always have. And sometimes it's because the function has all these exotic terms in it. Sometimes it's because the function has not been written out as a sum of products like this. Like, it hasn't been written out as a bunch of distinct terms. It's a bunch of other things multiplied together or something. Or, and this is a case we'll have to address in a separate lecture, we're analyzing a recursive algorithm and the running time is a recursive function. And so it's not always as simple as glancing at it and saying, oh yeah, there's n cubed, because maybe the highest order term is not obviously visible in the expression that you're looking at. So anyway, a function like this one here, so again, this is just a sum of products. So we've got 5n squared plus 100n plus 10,000 times log n. We can see, or I mean, the plots are a way of intuitively justifying this, but it's eventually going to be dominated by its largest term. And in this case, it is true, in fact, that f of n asymptotically approaches 5n squared. Now, this relationship of saying that something asymptotically approaches something else is interesting, and there are those that do use this as their main criteria for analyzing algorithms, but we are not going to be among those people, because I think, and I think a lot of other sources agree with me, that the relationship of f asymptotically approaching g is a little bit too strict for our purposes. And I've got a few ways of justifying this, but one of them is actually just that if I talk about this function f and the fact that it asymptotically approaches 5n squared, Didn't I say at the beginning that the goal today was to find some way of getting rid of constants? Don't I just want to talk about n squared? I don't want to worry about the difference between 5n squared and 4n squared, unless, of course, there's a tie. If I have two algorithms and one of them has running time 5n squared and one of them has running time 4n squared, well then, of course, that difference is now significant. But if one of them has running time 5n squared and one of them has running time 4 times n times log base 2 of n, well then, I don't want to have to worry about those constants when I'm comparing them. I want to compare them only based on the rate of growth relative to n. So if I use this relationship that f asymptotically approaches 5n squared, then suddenly I am responsible for those constants being realistic, and that would poke a few holes in my scheme of using a hypothetical architecture. Okay, there's that. There's also the fact that the definition of f asymptotically approaching g, we should know about this, but we're not going to use it very often directly. So when I say that f asymptotically approaches something, I usually write it like this, with this symbol here, and you can sort of appreciate that this symbol is often also used to describe approximations and things, and so it sort of fits well with that. But f asymptotically approaches g if and only if this limit converges to 1. And that makes sense because the idea of asymptotically approaching something as n goes to infinity does sort of imply a limiting case. The issue with using a limit here is that sometimes we work with functions that aren't as well behaved in this context as we would like. That is, if the limit converges to 1, then f asymptotically approaches g. But because I said if and only if, there are cases where the two functions are effectively in the same asymptotic category, but the limit doesn't converge due to just annoying factors. So one example is, what if for some reason one of the two functions contains the sine function? Well, you know, we do know that the sine function itself is always less than or equal to 1, but the problem is if we use the sine function in some limit, it may not converge for reasons that have nothing to do with the fact that it's greater than 1 or anything else. That's the issue. Using a definition that's based on a limit can also cause us some headaches later. So I've got two reasons that I think that the relationship that f asymptotically approaches g isn't quite what we want for our purposes. All right, so let's take a look at this stack. I hope the color resolution on your monitor is nice because there are a lot of different colors in this plot. But don't worry, we don't care that much about any of these functions. I just want to show what happens as I zoom out. So I have this huge stack of functions. I've got, I'll run through them. So I've got f1, that would be this line here, is 10n squared minus 100n plus 1,000. And of course, we can see that that asymptotically approaches 10n squared. That's the dominant term there. I've got f2 of n, that would be the orange line here, and it's going to be, the dominant term in it happens to be 1 over 5 times n. I've got f3 of n, that would be this green line here, so the one that ends right there, and it's asymptotically approaching 2 times n squared. What I will observe, though, just before we actually zoom out and see this is, so far we've seen that f1 and f3, so these two lines here, are both asymptotically approaching something times n squared, versus the orange line in the middle asymptotically approaches, so this would be 1 over 5 times n. So notice how this thing that the dominant term is just n to the 1, is in the middle of the other two, and that's just because of the constants that are involved. Then I've got f4. F4 would be this darkish red line here. It approaches 50n. So it and the orange line are both things that approach some function of n by itself, n to the 1. And then finally f5, which approaches 1 over 50n squared. So that constant 1 over 50 is going to make f5 pretty small. Let's see, where is f5 on this? I think f5 is this one here. All right. And so what I want to do, and that's a lot of functions. There's a lot going on here. But don't worry about it. All I want to do is show what happens to all of these, this big family of functions that they're sort of two different groupings of functions. They're the ones whose highest order term involves n squared, and there are the ones whose highest order term involves n. And what I've plotted separately on this plot are two lines that are just n and n squared. The brown line here is the line for n, and then up here is the line for n squared. All I want to do with this visualization is to show that as I keep zooming out, the differences between each family of functions become irrelevant. So it doesn't matter too much if, so f2, for example, with its 1 over 5 times n, and f4 with its 50 times n, it turns out that at the end of the day, as I keep zooming out, those are both going to be the same. So let's keep zooming out. Okay, I zoom out and I'm looking at 10 to the 20, which as I said before, is a respectably large number. I look at 10 to the 20, and by 10 to the 20, the two groups have resolved themselves into two separate channels. And actually that happens somewhere before 10 to the 6, I guess, sort of around 10 to the 4, but it doesn't really matter because we're zooming out to infinity here, so 10 to the 4, 10 to the 8, whatever. So I have these two distinct groups, the functions that are proportional to n, the functions that are proportional to n squared. And within the groups, there's quite a bit of diversity, so 10n squared, 1 over 50 times n squared, but it makes no difference. Ultimately, they've all grouped together pretty tightly, but I'm going to keep zooming out. Okay, so I'm going to zoom all the way out and I'm going to look at x goes up to 10 to the 100. And by now, they're actually still a little bit different because we can see they're not the same. It's not looking like one line. It looks like one sort of thick line because there are different functions there. But basically, they've grouped together so tightly that those constants don't make very much of a difference, especially if I want to compare something in this group to something in this group. It doesn't make much of a difference if I want to compare 1 over 50 times n squared to 50 times n. Those constants make no difference. It's the n and the n squared that make the difference. At a resolution that's this high, so talking about 10 to the 100, n is going to be faster than n squared. And I think it's this intuition that I want to carry forward. The idea that, yes, it happens to be true that f1 asymptotically approaches 10n squared. And it's also true that f3 asymptotically approaches 2n squared. And it's true that if I narrow down the contenders only to these two, then yes, I may actually care about the 10 versus the 2. But until I reach that point, I only care about the fact that they're both asymptotically approaching something times n squared. I also want to bring back up this idea that even if it's the case that they're tied, and I want to compare the two of them together, the 10n squared versus the 2n squared, even then, it isn't really possible to develop some analytical expression that captures, where we can be assured that that 10 is legitimate. We actually can, when we compare two algorithms that are both more or less n squared, we can do analysis that tries to ballpark the constant in front of it in a way that separates two functions where the constants are dramatically different. But usually it's the case that if on my hypothetical architecture I'm looking at 5n squared versus 4n squared, that's probably a sign that on any real architecture it's a bit of a toss-up as well. And even if we do analyze it on a real architecture, we don't know whether an analytical expression would actually give us a constant that we could rely upon as breaking that tie. That is a case where you might want to use a timing experiment. When you have two algorithms that have the same, that are asymptotically approaching the same function of n, and where it's not obvious that one of them has more overhead than the other, that is where you might just want to do some timings, when you've narrowed it down to that point. So at a massive scale like this one, and actually not just at this one, but even back at 10 to the 20, or even back at 10 to the 10, at a massive scale, these different functions have resolved themselves into very tight groups, and the grouping is based only on the function of n. It doesn't really matter that much what constants appear in front, and it doesn't matter that much what, so I mean, this n squared here is all we care about for f3. We don't care about the 2, we don't care about the lower order terms. And so, of course, the slide's catching up, I guess, to what I already said, but compared against the other functions, the three that are related, that are in the n squared family, f1, f3, and f5, are basically equal. And I think that we should come up with a way of measuring, we should come up with some notation that allows us to say that asymptotically, f1, f3, and f5 are equal to each other. We need basically an asymptotic generalization of an equal sign. And we've got it. It's this. This is the capital letter theta, and we're going to call this thing Big Theta. And it is used to describe asymptotic relationships that are equal up to a constant factor. Now, the notation for Big Theta is, although Big Theta functions sort of like an equal sign, it doesn't look like that when you write it down. So I write it down like this. I say, when I want to say that, so let's use an actual function here. So I can say 10n squared plus 5 is Big Theta of 7n squared. And actually, more generally, what I would more likely write is something like this. 10n squared plus 5 is Big Theta of n squared. What I'm actually saying is that 10n squared plus 5 and n squared are asymptotically equal up to a constant factor. And this equal sign is not written like a typical equal sign. It's written with a set inclusion operator, a set membership operator. That's because Formally, when I write big theta of n squared, I'm referring to the set of all functions that are asymptotically equal to each other and equal to n squared up to a constant factor. So big theta of something actually refers to a whole set of things. And when I say 10n squared plus 5 is big theta, I'm actually saying 10n squared plus 5 is one of those functions. It's a member of that huge infinite set of functions that are asymptotically equal to n squared up to a constant factor. Okay, that's all weird. That's going to take a while to get used to. Many of you have come out of first-year programming already familiar with asymptotic notation in a broad sense, in an intuitive sense. You've probably seen big O. You've probably heard somebody describe an algorithm as being big O of n squared or big O of log n. Big theta is a member of that family of operators. So I would read this as f is big theta of g, and I would read this as 10n squared plus 5 is big theta of n squared. And so we think of this, and I encourage you to think of it this way. Mentally, when you see this, think about an equal sign, because this behaves like an equal sign. So in this case, we could say, because F1, F3, and F5 are all members of this grouping, they're all members of this family, they're all asymptotically approaching something times n squared, that means that F1 is big theta of F3. It also means that F3, that's a weird 3. F3 is big theta of F1. And it means F1 is big theta of F5. And like any other equal sign, if A is equal to B, then B is equal to A. So if F1 is big theta of F5, then F5 is big theta of F1. And if I recall correctly, the slides are actually going to say the same thing, but type it out nicely. Yeah, there we go. So it's also true that F of the family F1, F3, F5, F3 is big theta of F1, F5 is big theta of F3, F3 is big theta of F5. I mean, there's lots of combinations you can make here. They're all members of the same family. They all share an equal sign with each other. Now, so most significantly, the big takeaway here is that of the members of that family, so we've got F1, F3, F5, and then the sort of reference line for n squared, the one that's the easiest for us to talk about is n squared. And so the common practice isn't to write something like, oh, F1 of n is big theta of 10n squared plus 5,000. That doesn't really make much sense to us because our whole goal here is to avoid worrying about constants. Although this is true because F1 of n does asymptotically approach something times n squared, and so does this. What I would typically write actually is just this. And this is the most significant takeaway here, is that all of the functions in the n squared family are big theta of n squared. And that means by writing it this way, I've boiled them down to their most significant aspect. That is the rate of growth, n squared. And so we can say they're all are broadly quadratic. All three of those algorithms are broadly quadratic in the input size n. I guess I should add the slide didn't say this. That wasn't very courteous. But it turns out that the functions in the n family also have the property of being big theta of each other. So that would be F2 and F4. So I can write that F2 of n is big theta of F4 of n, and vice versa. F4 of n is big theta of F2 of n. But actually what I care about really, I mean, they are big theta of each other, but the big takeaway here is they're both big theta of n. They're both basically linear. When I think of in the asymptotic case, they're both basically linear. Okay, so here is a slide reminding us why big theta can be treated like an equal sign. It actually obeys all of the same rules as an equal sign. So like a regular equal sign where I'm allowed to say that a equals a, so for any value, that value does equal itself, it is true that any function is big theta of itself. It is symmetric because we know that if a equals b, then b equals a. And similarly, if f is equal to g, or if f is big theta of g, then g is big theta of f. We also know that equals is transitive. If a is equal to b and b is equal to c, well, that means a is equal to c. They're all equal to each other. And then the big theta version of that, it's notationally a bit verbose, but if f is big theta of g and g is big theta of h, then f is big theta of h. And h is big theta of g and h is big theta of f. So applying combinations of these rules together, we can actually see that any property that we can apply to an equal sign actually does apply to big theta. It's what's called an equivalence relation. I really encourage people to think of big theta that way. I find that it seems, so going back a long way, even when I was a student, it was often the case that people that were very talented as computer scientists did not enjoy learning about algorithm analysis. And I think one of the reasons for that, and it was true for me, getting used to big O and big theta and things, it had to do more with just all of the symbols, all of this weird stuff, and being given all of these definitions that are very crisp and mathematical, but very hard to reason about. If I had understood at the time that big theta was like an equal sign, it would have made it a lot easier for me to sort of play around with the concept mentally, to think about what that means. So think about that. It is theoretically true, it is formally correct that big theta behaves like an equal sign. It has the same relationships as equal signs do. So think of it that way. It may make your life easier. So here is a definition. Well, I shouldn't say definition. A sufficient condition. It is not a necessary condition, and I'll come back to that in a few minutes. I'm covering a few bases at once in this lecture, and I have to come back to a few things. So one way of asserting big theta, so a sufficient condition, is this limit. If the limit of f over g converges to any constant that is, well, any non-zero constant, and we'll come back to the case where it equals 0 later. If the limit converges to any positive constant c, then the two functions are big theta of each other. And you can observe that, of course, the limit of if the limit of f over g converges to c, then the limit of g over f converges to 1 over c, which is still going to be a positive constant. This symmetric relationship will still apply. This is a sufficient condition, which is to say that if the limit converges, then it is definitely true that f is big theta of g. However, it is not a necessary condition because there are cases where f is big theta of g where the limit doesn't converge. And I hinted at this earlier, but that often has to do with the fact that the limit isn't converging because f or g are ornery. They're functions that don't take well to limits, not because they're not big theta of each other. So we'll come back to the actual formal definition, the full definition of big theta, in something like 30 slides from now. So it's also true, while we were talking about that asymptotic analysis, or asymptotic relationship, the idea of f asymptotically approaching g, if f asymptotically approaches any constant times g for some constant that's positive, then f is big theta of g. So just to be clear about that, let's take a look at some functions. So let's do f equals 10n squared plus 5, and g equals 2n squared minus 7. Okay, so a couple of points. F does asymptotically approach 10n squared, because that's the dominant term, and g asymptotically approaches 2n squared. Is it true that f asymptotically approaches g? And the answer is no. So f does not asymptotically approach g because 10n squared and 2n squared, if I take the limit of them, the limit is not 1 as I go to infinity. However, f does asymptotically approach, so let's see, so f is equal to, I'm going to write this as 10n squared. Well, 10n squared asymptotically approaches, I think you'll agree with me here, 10n squared. And I could write 10n squared as 5 times 2n squared. And I can observe that this is basically me saying that f asymptotically approaches 5 times g. And that meets the definition for the theorem, which means from this aspect here, because I found a constant c, this implies that f is big theta of g. And of course, that means that g is big theta of f, because big theta functions like an equal sign. Or if I wanted to prove that g was big theta of f, I could go and find a constant, and that would just be 1 over 5. I'll spoil it for you. But this is one way of relating our more strict definition of f asymptotically approaching something to this idea of big theta. But going forward, I'm going to use pretty much big theta all the time. I want to talk, what I haven't given you yet is an actual definition of big theta, as I said. I have defined a sufficient condition, and I've given you this theorem to relate it back to asymptotically approaching things, but I haven't actually given a full definition. I'll do that in a few minutes because it's easier once we have more things. Okay, so let's go back to these contains duplicate algorithms, and I swear one of these days we will be done with these. We're going to move on to much more interesting things pretty quick. But here are 3 analytical running time expressions that we derived in the previous lecture. So we've got our original nested loops algorithm, our improved nested loop algorithm, and the sort and scan algorithm, and they have these 3 running times. We can use the theorems on the previous slides to show that f1 is big theta of n squared. We can do this in a bunch of different ways, but I think I would probably just, if I had to use one of them, I would probably just use the limit for these, because these functions are reasonably well behaved. So I could show that this over n squared converges to a constant. I guess it converges to 4 as n goes to infinity, so that means this is n squared. This is big theta of n squared, and this turns out to be big theta of n log base 2 of n. All right, good. So this is nice because it allows us to talk about these three algorithms in a very abstract sense based on the rate of growth as n increases. Somebody who's asking me which algorithm is faster between these three doesn't care that much about that plus 2. They don't care about this plus 2. They don't even care about that 4 or this 10. What they care about is, if I were to plot all of these and keep zooming out like I have done here, they care about which of the three functions falls into, as I approach infinity, as I keep making my inputs larger and larger, which one falls into the lower, has the line that is going to come in lower. That's pretty much it. And we understand that if they are not asymptotically equal, so if they are not all big theta of each other, then there should be some separation that grows over time. They should end up in separate groups. And of course, maybe reading a little bit ahead here, we can observe that we sort of already knew this, but this finally gives us the ability to say, okay, F3 is probably the best. As far as running time goes, we understand that because intuitively, and we can justify, we actually will justify this formally in a few minutes, but because it's the case that log base 2 of n is, and I will use the quotes again, less than n, then it's reasonable to assume that n log base 2 of n is less than n squared. Now, maybe you're seeing me put less than signs in quotes and thinking, you know, what we need is some asymptotic version of the less than sign to go with our asymptotic equal sign. And I think so too. So we can see that F1 and F2 are asymptotically equal. They're big theta of each other up to some constant factor, which does reflect reality because we can see we've got 4n squared versus 1n squared for F2. We can compare those two to F3 and say, well, it does appear as if F3 is faster, but we don't quite have a way of doing that formally. We don't have a way of actually comparing F1 and F2 to F3 formally beyond sort of glancing at it and saying, well, I'm pretty sure this is better. So we need an asymptotic version of our other comparison operators. I mean, at minimum, we need a less than or equal to operator, but I'm sure you'd agree that if we have a less than or equal to operator, we'll get a greater than or equal to operator for free. We just flip it around. And while we're at it, we might as well define strict inequality operators as well. Although it's pretty much true that in this course, we're going to use the asymptotic equals operator and the asymptotic less than or equals operator pretty much all the time. Rarely do we need the other ones. We do occasionally need this one, but not that often. So here they are. Here's the complete family. We have the strict inequality less than operator. It looks asymptotically like this. We call this little o. And then we've got the less than or equal to operator, which is this one, which we call big O. And I will admit that I am sort of annoyed by many other sources, in fact, pretty much every book on algorithms that I've ever seen, which likes to call big O this. And I just don't understand. I don't understand. So I'm not going to do this. It's a big O. So we'll call it big O. It just seems obvious. Anyway, big O. And then we've got big theta, which is our asymptotic equals sign. And then we have here, this is the asymptotic greater than or equal to sign, and it is written with this symbol. This is the capital letter omega, so we write it big omega. And then down here, this is a neat one. Greek letters are pretty interesting. This is the asymptotic greater than sign. This is the lowercase omega. It doesn't bear much of a resemblance, but it is in fact lowercase omega, so we call it little omega. And here's a piece of trivia. This is the kind of trivia that's clever to know, but that nobody thinks you're clever for telling them. It just makes you sound sort of annoying for telling them this. But it turns out that the reason, like you're wondering, why the fancy Greek letters? These look pretty cool. And then we just have an O here, an English O. Well, it actually isn't. So I believe originally this, what we call big O and little o, which we should just call big O and little o, actually this is another Greek letter. It is this one. And I'm going to pronounce it Omicron, although I understand that that's a function of my accent, pronouncing it that way. It is, in fact, the Greek letter, the capital Omicron and lowercase omicron. But the kind of people that go on about that can sometimes be a bit much. So we just say big O, because that's what it looks like. We don't need to know Greek to understand how to use big O, and we know enough about the Greek letters theta and omega to be able to use those too. Okay, so let's talk about big O. So that is our asymptotic less than or equal to sign. And here is the real definition, the actual formal definition of big O. And this is a bit tough to digest at first. It's important that we have this. It is really important that we have this. And you know, I don't think it's that bad eventually. Once you get used to it, this definition turns out to be all right. However, I'm happy to admit that I don't think that I really wanted to fully digest this definition until I was like a grad student or something. That is, I did just fine in algorithms courses. I was able to use big O, but I didn't feel that I was very comfortable thinking about big O with this definition or writing proofs with this definition. And the reason for that, frankly, was that I don't think the people that taught me it liked it very much themselves. I think that they weren't very comfortable with this kind of definition, and they were trying to find a way around talking about it intuitively because they didn't like it any more than I did. Looking back on it now, I don't think this definition is very threatening, but that's exactly the kind of thing you'd expect somebody like me to say. There's nothing more annoying than some patronizing instructor being like, oh, all this is really easy. This all takes you the homework only takes you 10 seconds. The reason that I'm comfortable with this definition is because I've used it over and over again. And over time, I guess, the meaning of each of these constants is sort of locked in my brain. So what I suggest that we do is as follows. We have to know the definition, and that means, and the reason for that is that we have to understand what this definition is saying, why we've defined big O the way we have. However, you will discover, as we'll see in a few minutes when we do some exercises, that even though we have this formal definition, there are lots of ways of asserting that f is big O of g without needing the definition directly. Consider, I can't remember this off the top of my head, but all of you know calculus to some extent. You know differential calculus. You can compute derivatives. When you take the derivative of a function, I'm not going to do this. I should know better than to try and randomly do calculus in the middle of a lecture. But so here is a function here. Take the derivative of this function. And then tell me whether when you took that derivative, did you use the formal definition of a derivative? Because the formal definition of a derivative, and I'm not going to try and write this out because I don't remember this, is a limit. It's the limit as some parameter goes to 0 of a difference, of some ratio. Do you use that when you compute derivatives? Do you use that directly? You probably don't. In fact, when you compute the derivative of this f of x, you probably use a set of derivative rules. So there are lots of derivative rules. There's the chain rule, there's the product rule, things like that. That is how you compute a derivative. But actually, the definition of a derivative is some limit, some very important limit. I don't want to disparage that. I mean, even people that teach calculus would probably acknowledge that it's no fun taking derivatives with this limit most of the time. But having this limit is very important. It's important for lots of different reasons, one of which is you need a rigorous definition of concepts. That's one big reason. But also, what if there are times when your derivative rules don't work? The derivative rules are sort of like a paved road. Once the territory has been explored and you pave a road, anybody can drive between 2 points. So if once you build a city at location A and a city at location B and you pave a road, it's easy to use. And once people solved the problem of how do you take derivatives of continuous functions like these, then they designed all these derivative rules and said, hey, if you want a derivative, just use the rules. They paved a road for everybody else to use. However, sometimes in mathematics, you discover a new kind of function or you discover a new kind of relationship, and that's you wandering around in the wilderness, and then you discover some oasis out here called C. And getting to C for the first time can be rather treacherous before the road is paved. We need the definition to know how to go exploring in the wilderness. The same is true of big O. The reason we need a formal definition for big O is that we need something that we can use if all else fails. Some basic truth about what big O means. So if we're analyzing some really exotic type of algorithm or something we haven't seen before, we know how to do that. But in practice, we often find ourselves using much more convenient ways of applying big O than this definition. Okay, but I actually haven't talked about the definition yet. I was so excited to give my analogy about building roads that I didn't do that. So suppose we have two functions f and g. If there exist two constants, and they're going to be c, and I'm going to read this one as n naught, such that f is less than or equal to c times g for every value of n larger than n naught, then it is true that f is big O of g. So as before, the big O, when I write big O of something, So for example, this big O of n squared. This is a set of all functions that are asymptotically, you could say, less than or equal to n squared. This is a set of functions. So when I say that one particular function is big O of n squared, I write it with set membership. I say n squared is one of those functions that is asymptotically less than or equal to n squared. And I read this expression as f is big O of g, or 10n squared is big O of n squared. Now, an interpretation, which isn't very useful without a diagram, without a visualization, is that if there is some multiple of gn such that beyond a certain fixed point, f is always less than that multiple of gn, then f is big O of gn. And as with any other thing, this is a symbolic description of something that we should be visualizing, so let's go visualize it. So big O is an asymptotic generalization of the less than or equal to operator, and critically, it behaves the same way. I said a few minutes ago that I don't think that as any other computer science student would do, I had to use big O all the time as a student. I mean, it shows up in algorithms courses, and it shows up in pretty much every course after that. It shows up in plenty of courses that don't analyze algorithms because we need to talk about how long algorithms take. And as a student, I was able to use it. It was fine. But I don't think I was as comfortable with it as I should have been. And I think one of the reasons for that was that pretty much nobody else was either. It's very difficult to become comfortable with it unless you think about it intuitively. So intuitively, it is a less than or equal to sign. And that means all of the usual rules apply. So if f is big O of g, and g is big O of h, well, then we can expect, just like how if I know that A is less than or equal to B and B is less than or equal to C, that means that A is less than or equal to C. Similarly, if F is big O of G and G is big O of H, then F is big O of H. So like any other less than or equal to sign, all the same relationships apply. It's similar to how big theta functions as an equal sign. And it turns out these generalizations apply to all of the different asymptotic operators, all the different asymptotic classes. So big O, big theta, big omega, little o. So what we can do here, so let's take a look at two functions. Basically, I want to show how to employ that definition. So here's an example where I've got two functions f and g. It makes no difference what they really are. And of course, this plot is just for visualization. That's why I'm not telling you the functions, because we can't just use a plot to decide if big O applies. We have to write a proof. But if I happen to be in a situation where g is literally always less than or equal to f, I mean, that could happen, that the actual less than or equal to operator applies. If that happens, then clearly g is big O of f. And the way we know that is I can choose a constant, so I can write g of n is less than or equal to f of n. If that happens to be true, well then of course it's true that it's less than or equal to 1 times f of n. And it's true for all n greater than 0. And the idea is this is our constant c, and this is our value n naught. For every value of n greater than n naught, which in this case is 0, it is true that g of n is less than or equal to 1 times f of n, so c times f of n. Now suppose we want to show that f of n is big O of g of n. And you can see here that it doesn't look that plausible that it is. I mean, there's f of n there. It's larger. It appears to be larger. But as you know, plots always lie or whatever. So what I could do is this. I find some multiple of g of n such that that multiple, so c times g of n, that would be this curve here, is larger than f of n forever. So there becomes a point at which c times g of n is always going to be larger than f of n. So I find a constant such that I can make g of n get bigger than f. And then I find some point after which, so for all points to the right, all values of n greater than this point, c times g of n is greater than or equal to f of n. So that's the geometric or the graphical meaning of c and g. So I choose a constant n naught such that after n, for every n greater than n naught, c times g of n is greater than or equal to f. Now, it's tempting with this visualization, so if I go back by 1, to say, oh, okay, I need a value of n naught such that every greater value of n is, I have f of n is less than or equal to c times g. So we'll choose the exact intersection of those two. You could do that, but do you really want to waste time doing that? In this case, although we shouldn't use visualizations for this, I could observe that this is a perfectly valid n naught. I mean, it is true that for every value of n greater than 50, if I believe the plot, f of n is less than c times g of n. There's no requirement that n naught be chosen to be the minimum possible value at which that condition applies. It can be chosen to be whatever's convenient for you. And the slides agree with that. I should have let the slides do the talking for me. So here is a theorem based on limits that is a sufficient condition. We saw this with Big Theta earlier. So with the Big Theta theorem, it was if the limit converges to some constant greater than 0, then f is Big Theta of g. But here, if it converges to some constant greater than or equal to 0, then f is big O of g. And it's neat to see this because this greater than or equal to instead of greater than is basically a way of acknowledging that when I'm saying A is equal to B, I am saying something distinct from when I say A is less than or equal to B. A is allowed to be less than B if I am working with big O, versus big theta where A and B have to be within some constant multiple of each other. And we'll actually see in a few minutes a case where we have the constant actually is required to be equal to 0 for a different asymptotic class. So this theorem is a sufficient condition, and it's very useful. And I bet that most of the early proofs that you have to write for big O, you will probably want to use this. Even if you hate limits, you'll probably want to use this, because you do know limits already, and the limits that we have to do in this course are probably a great deal less horrifying than what you had to deal with in Calculus 1 or Calculus 2. And the advantage of this condition is because usually the expressions we work with are continuous functions, that is, they're relatively civilized functions like f of n equals tan n squared plus log n or something. These are things that limits can be computed for relatively easily. There are, unfortunately, going to be cases where that doesn't happen, where f of n is some irreducible sum or something, or it's a recursive expression, and that means we can't use the theorem if we can't compute a limit. But when the limit does exist, then we can use the limit as a way of asserting that it's big O. Remember, though, that the theorem is not a necessary condition. So there could be cases where the limit doesn't exist and f is still big O of g. And so you can't draw any inference from the limit not converging. If the limit doesn't exist, that doesn't mean that f is big O of g or that f is not big O of g. It just means nothing. But if the limit does exist, then you can use that and you can employ this theorem. So let's do a few of these. Prove that 6n squared is big O of n squared. There are a couple of ways of doing that, so I'll remind us that we have two options here so far. We have this theorem that lets us use a limit, which just says put them one on top of the other and take the limit, or we can use the definition directly. And I have written, for all of the different exercises I want to go through today, I've written proofs that use both, because we should get used to using both. Even if we have a favorite, you should know how to do both, and you should know how to read a proof that uses either. Generally speaking, if I ask you to write a proof, I'll ask you to write a proof like this. I'll say, prove it. And it's up to you how you prove it. Of course, it's your responsibility for the proof to be correct and to show all the steps, but you can use any method that you want. Okay, so prove that 6n squared is big O of n squared. Okay, let's try that. I think there's two different ways of doing that. What I can observe is this. Okay, would you agree that 6n squared is less than or equal to 6 times n squared for all n greater than, oh, I don't know. I could say 0 here. I could say any number I want. Let's do n greater than 1. If that's the case, so this is my proof. So taking c equals 6 and n naught equals, for the sake of variety, let's do 3, because I'm allowed to use any value for n naught that I want. N naught, well, as long as it meets the criteria. N naught equals 3. We have 6n squared is less than or equal to c times n squared for all n greater than n naught. And therefore, that implies that 6n squared is big O of n squared. So my proof consisted of showing how to apply the definition. So I provided a value for c, and I provided a value for n naught, and I stated this. Now, this is something that it is reasonable for us to simply say. We do not have to justify why it is that 6n squared is less than or equal to itself. There are, however, versions of this proof where we're proving something a little bit more controversial, where we do have to explain where we're getting our reasoning from. And I'll show a couple of examples of that in a minute. I could prove it a second way, though. I could use the limit. Okay, so we'll remind ourselves of the limit condition. It says if f over g converges to anything at all, if it converges to some constant that's greater than or equal to 0, then f is big O of g. So I put the thing, if I want to prove that 6n squared is big O of n squared, I have to put the n squared as the denominator of my limit. So let's compute the limit. So the limit as n goes to infinity of 6n squared over n squared, Well, fortunately, it's not fun to do calculus in public, but fortunately this is going to be a relatively easy one. This is going to end up equaling 6. And I can observe that 6 is greater than or equal to 0, and that's actually all I need to write. We understand that there's that theorem that tells us that we can use this limit, as long as I use the limit correctly, of course. Therefore, I've got 6n squared is in big O of n squared. A minute ago when I talked about that limit theorem, I said you're going to want to use the limit theorem. This might be enough to show you what I meant by that. Because some of the limits we need to compute are sort of obvious. Like the limit of 6n squared over n squared is not difficult. And writing it down is enough to prove that 6n squared is big O of n squared. All right, so for better or for worse, the slides did not use the same creative choice of n naught that I used, but you can see we have the same two proofs here, method 1 and method 2. All right, prove that n squared is big O of 6n squared. And what I will observe, we'll come back to this, but what I will observe is this. Suppose that you know that a is less than or equal to b, and then later you are able to show that b is less than or equal to a. Wouldn't you agree that that means that a equals b? I would say so. And what we're showing here, a minute ago we showed that 6n squared is big O of n squared. And now we're being asked to show that n squared is big O of 6n squared. And it sounds like that would mean that the two of them are asymptotically equal. And actually it does turn out, although we haven't seen why this is true formally, it's not too much of a leap, it turns out that these two facts taken together are basically telling us that 6n squared is big theta of n squared. None of that should surprise us though, because we can see that if I ignore that constant, I'm looking at the same function on both sides. All right, but let's write this proof. In this case, let's see, I would say the definition is actually very easy to use here. Let's do that. So let's do proof. The limit's also pretty trivial, frankly. So these are both very easy. This should be a very straightforward exercise. So let's choose c to equal 1 and not to equal 0. Since n squared is less than or equal to c times 6n squared for all n greater than n0 or n naught, we have, since, well, I can just write it like this, n squared is big O of 6n squared. And that's it. That's my proof. Now, you might look at this and say, okay, then why do I need to write a proof? If it's this obvious, why do I need to write a proof? Well, it might have been obvious to you, but when I read this, it's even more obvious to me. That's why you wrote that proof. And if you're asked to prove it and you don't write what c is equal to and what n naught is equal to, you haven't used the definition. You've asked me to use the definition. Writing a proof involves doing the work. Even if the work is easy, that means it's easier to do it. And so yes, this proof is relatively simple. But if you didn't write this line, then you'd probably not get any marks for it. That's the way that has to work. Okay, so here's the two versions of this. You can see that this is essentially this is the converse. I don't want to say converse. This is the mirror image of the ones we already saw. So let's do a few more. Prove that n is big O of n squared. Okay, so this is a bit more of an interesting one because we can't fall back because I mean unlike 6n squared, like n squared is always less than or equal to 6n squared. So that's a bit of an easier one. N is not always less than or equal to n squared. So how do I do this? Let's do both halves. Okay, so proof. Let's try this. So what it's sketching out n and n squared. So here's n, and then there's n squared, more or less. That's not very good, but that more or less. So I observed that, I don't know, after some reasonable time, I guess after n equals 1, n squared is always greater than n. But just to be safe, I could even say n equals 10. So I'm going to say choose c is equal to 1 and n naught is equal to, let's do 1. Since we have n is less than or equal to 1 times n squared for all n greater than 1, then we have that n is big O of n squared. And we can try it with the limit. And so I say, let's take a look at the limit. Limit as n goes to infinity of n over n squared. And actually, I should do some copy editing here. I should always, when I write algebra in a proof, I should use English to explain where I'm getting the algebra from, or at least to introduce what I'm trying to do. Since the limit converges to, okay, well, the limit here is going to be, if I cross off an n, I can see it's going to be 1 over n as n goes to infinity, and that means that it's just going to converge to 0. We've got n is going to be big O of n squared. So I have to write the limit down, and in cases where the limit is more complicated, I have to explain where I got the answer. But that's it. That's my proof. Okay, so I think the slides did the same thing that I did there. Okay, prove that n is in big O of n log n, and well, log n base 2 in this case. So there's a couple of ways of approaching this. I'm not going to write this one out from scratch because I think we can see the pattern for now. But basically, in this case, the limit is way easier if you can contend with taking limits of log n base 2. The way you'd probably handle this if you needed to, well, you have a couple of ways of doing the limit. So maybe I should have written it out from scratch. So basically, one way of addressing this limit is to observe that it's basically 1 over log base 2 of n. And you can probably reason your way out of having to use like L'Hopital's rule here by just observing that this is an increasing function. That is, log base 2 of n goes to infinity as n goes to infinity. And 1, doesn't. So therefore, the limit goes to 0. And that should be enough. Alternatively, if you didn't observe that there is an n you could cancel out, you could take the derivative of both. That would require a derivative of this, which isn't the end of the world, but it's probably easier to convert it into base e first. But your mileage may vary. And then to do it with the definition method, well, okay, so for this, we have to be careful of a couple of things. So one of them is we can't evaluate a log at 0, which means we probably have to talk about n naught being at least 1. It's true, though, that it turns out that n, if we sketch out the two functions, so there's n, log base 2 of n, I can't do the best drawing of this, but log base 2 of n sort of looks like that, although that's giving it a bit too much credit, like that. And so it turns out they don't cross or anything, so all you really have to do is just to find a point where it's pretty obvious that they're both defined and that they're both separated. And we can do that so there's no need to have c, the constant multiple does not need to be anything greater than 1. And so you can see here we don't need very much extra algebra, we just have to justify our claim. Okay, so now prove that log base 2 of n is big O of n. And I'm going to shirk a little bit on this one too, because you can see that n being n being log base 2, n being big O of n times log n, and log n being big O of n have quite a bit in common. So let's do, I don't want to do the limit one for this. Yeah, we'll show off the result here. So in this case, the limit would probably be a bit of a pain. It'd be more trouble than it's worth. Now that said, so it's not worth too much trying to criticize one method over the other, because odds are you'll become comfortable with one method and want to use it all the time. If you like the limit version, it's true you'd probably rather use the limit version for this, even if it's a bit more tedious, basically, because it's easy to develop a routine. However, we can observe that we understand it to be common knowledge that log n is less than or equal to n for whenever log n is defined, for log base 2, and well, for logs of any base that we care to consider, log n is going to be less than n over time. That's actually why we're proving that log n is big O of n. So the definition probably is easier here because we're stating a sort of fundamental fact. And it's good that we've done this because we later in the course constantly want to use the fact that log n is big O of n, but actually justifying it isn't very difficult. In this case, the definition probably is a bit easier to use. Okay, prove that 10 to the 6 is big O of 1. Now this is, I don't know if I want to spend too much time on these exercises, but I guess I will do this one because it's sort of surreal. So, okay, let's try the limit version. Since the limit as n goes to infinity of 10 to the 6 over 1 is equal to a constant, that means that 10 to the 6 is big O of 1. All right, good. So that one's taken care of. Okay, and then what about the definition? This is sort of weird. Well, let's choose. Clearly, n naught makes no difference here because there's no n in either expression. Choose c to be equal to 10 to the 6 and n naught to be equal to 0. Since 10 to the 6 is less than or equal to c times 1 for all n greater than n naught, I mean, to the extent that makes any sense. We've got that 10 to the 6 is big O of 1. That shouldn't surprise anybody. So because the whole point of this asymptotic analysis is to avoid worrying about constants, any two constants are big O of each other. And you could also prove that 1 is big O of 10 to the 6, although that's frankly a little bit less surreal to prove. So here's this. I don't think we need to belabor this one any longer. Okay, prove this. Now, I could have written sine of n here, but just something doesn't feel right about that. Sine doesn't feel like the right function to use in a running time, so I'll use sine of x. Prove that sine x is big O of x. I did this for a reason. I'll show the two solutions, or the one solution. So the issue here is that this, well, wait a minute. Actually, I'm getting ahead of myself. Okay, so if I compute the limit, well, that's pretty easy. Sine x over x. Sine x is, of course, it keeps moving around, but we know that it's never any greater than 1. And that means that we can show that actually sine of x is actually big O of 1. And we'll do that in a minute. That's the thing I was getting ahead of myself for. So because sine x is less than or equal to 1 for all real numbers x, then I'll just choose c to be equal to 1 and n not to be equal to 1. And of course, after the value of, after n equals 1, the function x, or actually after x equals 1, the function x is always greater than 1. And so I can use that to apply the definition. That's actually pretty straightforward. But anyway, the next one is the one I was looking forward to. Prove that sine x is big O of a constant. Prove that sine x is actually big O of 1. We should understand that this has to be true because we know that sine x is always less than or equal to 1. So how do we do that? Okay, well here are two things we could try. So method 1 works. We do basically the same thing we did in the last exercise. We just choose c and n naught. We use the definition, but we can't do it with the limit. And there's the reason we need that formal definition. We need something to fall back on in unusual cases when there's no paved road. The limit condition doesn't work, but it's not really because sine x isn't big O of 1. It's because I've chosen a poorly behaved function for this purpose. The limit doesn't converge because sine x can't decide on a value for itself, pretty much. So sine x over 1, as x goes to infinity, it will always be between -1 and 1, but it doesn't converge to a constant like the theorem requires. So I just can't use the limit condition. Now it's true, if you look into this a bit, you'll see that there are lots of theorems we could state about big O that have to do with the limit supremum or something. Like there are other versions of limits that might apply in this case, but we don't want to worry about that, and I don't want to branch off and start teaching a calculus course here. We've got other things to worry about. We've got thousands more slides to cover on algorithms first. Okay, so now there's this one. Prove that this function f, and this f is pretty involved, is big O of n cubed. This is one that's worth looking into, actually doing this exercise before we see the solution. I'm not going to do the limit version because the limit version is pretty straightforward, but I do want to show a technique that's pretty useful for doing the definition version. So it looks like this. And in a minute, you'll see the typeset solution, so I'm not going to worry too much about my handwriting being bad. But f of n is equal to 5n cubed plus 100n squared plus n plus 10. And I think it's reasonable to say that it's, let's say, let n not equal 1. And I'm just putting, this isn't part of my proof, I'm just putting this here for a point of reference for us. So that means that if I consider values of n greater than or equal to 1, I think this is true. 5n cubed plus 100n squared plus n plus 10 is less than or equal to 5n cubed plus 100n cubed plus n cubed plus 10n cubed. So what I've done is I've just modified every term of the function to have n to be have n cubed as its order versus n squared or n or a constant. And then I just add all of these together. So that's 105, 106, 116, I think. So that's 116 n cubed. So what I'm saying is that f of n, just with this chain of inequalities, is less than or equal to 116 n cubed for all n greater than 1. So that's where I said let n not equal 1. So then let c equal 116 and n not equal 1. And then we'll say, therefore, well, yeah, okay. I will make sure I write the definition out, so I've dotted my i's and crossed my t's. So since f of n is less than or equal to c times n cubed for all n greater than n naught, f of n is big O of n cubed. And this is a useful trick to use because it's a little bit involved, but it's not that tedious, and it's relatively straightforward. The limit isn't that bad either, frankly, but the limit can sometimes be bad with functions that look like this. And so it can be quite helpful to use this technique. Basically, what we're doing is just glomming all the terms together by setting them all to n cubed, with the reasonable observation that n cubed is larger than n squared and n cubed is larger than n. All right, so there is method one. We are allowed to use without proof the fact that when n is greater than 1, n to the k is less than or equal to n to the k plus 1. So n squared is less than n cubed and so on. And so we can just do what I just did, which is switch over every term to be n cubed and then add them all together. And the result sort of falls out as a good choice for a constant c. Now there's the limit, which we could also do. And in this case, the limit wouldn't be so bad, but the reason the limit's not so bad is because the annoying thing is the numerator. If the annoying thing were the denominator, so if I wanted to prove the opposite, so if I wanted to prove that n cubed is big O of f, you'd have to show quite a bit of work to evaluate that limit, I think. So if you use the limit version on an exam, you probably would, this one here, you probably would have to show a little bit of work. I don't know that you need that much, but certainly for the opposite case, you would have to show all of your steps. And there's a risk when you evaluate limits that you make a mistake halfway through or something. So keep that in mind. The definition can be quite helpful, especially for these sort of polynomial-like expressions. Okay, there are some exercises. I have some more coming up in a future slide. We have to talk about a few other things before the lecture can end. So now there's big omega. So we've got big O, which is our big O, which is our less than or equal to sign. We've got big theta, which is our equal sign. And the last of the big ones is big omega, which is our greater than or equal to sign. And you'll look at, what you'll notice with this is that this definition is the same as the big O definition, but with this thing flipped around. So it's just like big O, you find a constant c and a constant n naught such that f is greater than or equal to c times g for all n greater than n naught. So it's the same as big O except for the direction of the inequality has been switched. And if that's the case, we say f is big omega of g. And we read it like this. So one thing you can observe here is that first, this definition is very similar to big O, as I said, and second, by the properties of less than or equal to signs, if I have a is less than or equal to b, well, I could just, write that in a mirror and I end up with b is greater than or equal to a. And we would expect the same relationship applies to big O and big omega. So if f of n is big O of g, then that's the same as saying that g of n is big omega of f because of the natural sort of intuitive generalization of the inequality operators that we're getting with these asymptotic classes. So if f and g are functions that are defined for all n greater than or equal to 0, then f is big omega of g if and only if g is big O of f, which means if you need to be able to prove big omega, all you really need to do is prove big O. So if you can prove big O, you've got big omega taken care of. And that's just because big omega is essentially the complementary operator to big O. So it's a greater than or equal to sign where big O is a less than or equal to sign. Now we are finally ready to actually define big theta. So I mentioned before that we've seen some theorems, but what is the formal definition of big theta? And I wanted to wait until now to give it because now that we have big O and big omega, it's way easier to state. So think about this case here. I mentioned this during the exercises. A is less than or equal to b, and we discover later that b is less than or equal to a. Well, those two things have to imply that a equals b. And the same is true of big theta. So if f is big O of g and f is big omega of g, that is to say we've got less than or equal to and greater than or equal to, well then the only option must be that they are asymptotically equal. So the definition of big theta that I like to use is that f is big theta of g if and only if f is big O of g and f is big omega of g. And what's neat about that is that means to prove big theta, if I can prove big O, I can prove big omega. And if I can prove big O and big omega, I can prove big theta. So actually, despite there being this whole big family of different operators, I only need to learn one proof technique. Now, here is a definition that people that want to state definitions from scratch would write. So people that do not want to rely on big O and big omega could also write this. Let f and g be functions. If there exist two sets of constants and one n naught, such that some multiple of g is less than or equal to f, and in turn that an f is less than or equal to some other multiple of g, then f is big theta of g. The exercise here, which you can take a look at and might be worth doing at some point in this course, is to prove that this definition is equivalent to the one in the previous slide. And what this is really saying, I'll give you this much of a hint, is it's pointing out that you can, if you read into this, you realize this looks a lot like a combination of the definitions of big omega and big O. So prove that that's essentially what's going on here. So here's some more exercises to do, including a few that are not so easy, that are not as straightforward as the ones that we saw before, because they involve these summations. So there's a couple of issues with the summation. So the problem with this summation here, I won't do this exercise, but I'll provide some useful commentary. The problem with this summation is that if you want to prove that this summation is big O of n squared and you want to use the summation, how are you going to evaluate a limit? I mean, you could prove using only the summation and the definition, you could prove that this is less than or equal to c times n squared. That actually is, there are lots of ways of doing that. The problem is, if you want to use the limit condition, how do you evaluate this limit? And I mean, the spoiler is you don't. How do you evaluate this? So there are a lot of issues involved in evaluating limits of sums that go to infinity like this. Go ahead and try if you want. There are techniques to do that, but you'll find that the limit condition is not really helping that much in this case. So one option you have, which you don't always have, so it's useful to learn how to prove that a summation is big O of something directly without finding a closed form, but an option we have in this case is to observe that this sum is our old friend from the previous lecture, and that we happen to know, because we've proven it, and we can invoke that theorem here. So you can't just generally make these things up. You have to explain where you're getting this result from. But by a theorem that we saw last time, it turns out that this is equal to, that this sum is equal to this thing, which we can just expand that a bit. And that's actually enough to say, okay, well, because the sum is equal to this, all we have to do is prove that this is big O of n. And that's probably an easier task, because we can use the limit definition, we can use the limit theorem on this closed form. So keep that in mind. If you work with a sum, occasionally you have the option of turning the sum into a closed form. Alternatively, you might have the option of turning the sum into something that's close enough to a closed form to do the trick. I want to foreshadow that a little bit. Yeah, let's try that. So here's the sum here. Suppose I didn't want to come up with a closed form for this sum. Suppose I didn't already know there was a closed form. I didn't want to write an induction proof. I could make this observation, and this is sort of taking off on that strategy I used before with that function, that polynomial f. 1 plus 2 plus 3 all the way up to n. Okay, so there are n terms there. Okay, and let's see. So that is less than or equal to n plus all the way over plus n. So in other words, n of these, which equals n squared. There we go. So, I mean, I still need to show a value of c and n naught, but notice that just by using the regular less than or equal to sign, I was able to reduce the sum I was able to wrangle it into a form that's easier to work with. I didn't have to write some big induction proof that showed that the sum is exactly equal to anything, because I'm not proving that it's equal to something, I'm proving that it's big O of something. So keep that in mind. And you could use this trick pretty effectively in all of these, although the big omega cases are a little bit more complicated than the big O ones. And then there's a couple more exercises. And these ones, we'll come back to this. This can be not the most pleasant thing in the world. Okay, I have two more things left to talk about, though. So I haven't yet talked about the strict inequality operators, the less than sign and the greater than sign, little o and little omega. So let f and g be functions that are defined for all n greater than or equal to 0. And the definition of little o, I distinctly remember this was a case sitting in my algorithms course, the equivalent of this course, where I completely glazed over. I had no idea what was going on. Like, it didn't make any sense to me what real difference existed between little o and big O. So I'll state the definition, and I will say, don't worry about it. This definition, I think, is a bit impenetrable until you have some way of visualizing it or working with it. So what this says, the definition for big O is if there is any constant, just one of them, one constant, such that f is always less than or equal to g of n after some point n naught, then f is big O of g of n. For little o, it is saying if you choose any constant you want, so even a tiny value, any constant, if it's the case that for any constant you choose, f of n is going to eventually be less than or equal to c times g, then f is little o of g. And one way of maybe sort of sketching a visualization of that is this. So let's consider this situation. I've got a function that's basically n squared, and then a function that's also basically n squared. So I've got, here's n squared, and here's n squared over 10. Well, we know that this function and this function grow at about the same rate. It's true that 1 over 10 n squared is big O of n squared, and it's also true that n squared is big O of 1 over 10 n squared. And so that makes sense because this is the asymptotic less than or equal to sign. And so there is a constant I could multiply this by that would make it bigger than n squared eventually. Like if I multiply it by 100, then 10n squared is bigger than n squared. Now consider this case here. So suppose I consider this function. This is just n. It doesn't matter what constant you choose, any constant at all. There is no constant you can multiply n by such that n squared will not eventually be bigger. So any constant at all, there is no way to make to make n bigger than n squared forever. Right? You can make it bigger for now, but eventually n squared will always catch up. That basically is the intuition behind the definition of little o. Little o is saying if g is so big, if it's growing so fast that no matter what constant you choose, even a really tiny one, f will always fall behind, well then I guess you could say then that f is really less than g. It's not going to catch up. There's nothing you can do to make it catch up. They're not similar. F is less than g. So if there is no constant you can come up with that puts f ahead of g forever, then f must be much smaller than g. F is growing much more slowly. That is little o. But even that isn't easy to work with. There's a better definition that I use all the time, and it's the one internally, when I think of little o, the only one that I think about, and it's this definition. And unlike with big O and big omega and big theta, the limit is a definition. So unlike the other cases where the limit was only a sufficient condition, for little o and little omega, the limit is in fact a definition. So if f over g goes to 0, then f is little o of g. That's it. So even if there are weirdly behaved functions, so for example, if you think about the case of sine x over 1, that limit doesn't converge. But actually it's true that sine x is not little omega of 1. Sine x is actually big theta of 1. So maybe that makes your life easier. Maybe the fact that a limit is now the definition, which means you can always use the limit. If the limit doesn't exist, then it turns out that it's not little o. Only if the limit exists and converges to 0 is f little o of g. Okay, so little o is sort of the asymptotic less than sign, and we now have enough information to begin to talk about sort of forming a hierarchy of different common functions. So any constant c is big theta of 1, because all constants are within a constant factor of each other. Any constant c is little o of log n, and actually this should be, to be clear, log n in any base, any base greater than 1. Log n in any constant base is actually big theta of log n in any other constant base. And the reason for this is because if you want to change the base of a logarithm, you can do that by multiplying it by a constant. So logarithms in two different bases are always big theta of each other. In this course, we do pretty much all of our logarithms with base 2, but it doesn't matter because logarithms in base 3 and logarithms in base 2 are big theta of each other. They're asymptotically going to be equal. They're within a constant factor of each other. And that has to do with the law of logarithms as well. Like that's actually implied by the law of logarithms. Log n is going to be little o of n to any power, any constant power. And that's true even if the power is small. So to be clear, log base 2 of n or log base anything of n is little o of n to the 0.0000000 whatever, 1. And it doesn't matter how small I make that exponent, as long as it's some constant greater than 0, log n is little o of it. And if you don't believe me, go try and compute the limit. And you'll find that the limit's not too difficult to compute. In fact, try proving this exercise. There's an exercise. Prove that log base 2 of n is little o of whatever number that is. And you'll find that if you try and compute the limit, it becomes really obvious very quickly why it is that it has to be the case. N is little o of n log n for any base of the logarithm. And that doesn't surprise us too much, I guess, because we've seen n on both sides and because log n is an increasing function. N log n is little o of n to the k for any power of any k greater than 1. This is actually really sort of it sort of follows from the one 2 lines up. Any polynomial in n, so let's say n squared, is little o of n to the 2.1, or n to the 2.01, or n to the 2.0001, whatever. So any higher power of n will always be strictly larger than any lower power of n. And then finally, if I look at exponential functions, so q to the n, so one that we see occasionally in this course is algorithms whose running time is 2 to the n, big theta of 2 to the n. That's nasty. In general, any polynomial in n is going to be little o of anything to the power of n, which means that if I think about n to the power of, I don't know, let's do 10 to the 100, that is in fact little o of 2 to the n. And it's little o of the 3 to the n and little o of, and so is n to the, 100 to the 100. Any polynomial whatsoever is little o of 2 to the n, little o of 2.5 to the n, whatever, because exponential functions grow really, really quickly. Okay, one left. So little omega. So little omega is the asymptotic greater than sign. And this one will be easy because really it's just little o, but in reverse. It's a flipped version of little o. So this says if for all constants, if for every non-zero constant, every positive constant, there is going to be some n naught such that f is greater than c times g, well then f grows much more quickly than g, and we say f is little omega of g. And just like in the little o case, little omega can be equivalently defined using a limit. And so as you've seen, big omega and little omega probably aren't too much to worry about because if you understand big O, you can do big omega for free. If you understand little o, you can do little omega for free. But I want to state a bunch of relationships just to have them all in the same place. So all of the usual intuitive relationships of inequalities apply to our asymptotic operators. So here are some things that we know about regular inequality operators. For example, A always equals itself, and any value is always greater than or equal to itself. And if A is equal to B, then B is equal to A, and so on. And we can write the equivalent things stated with asymptotic operators. So any function is big theta and big O and big omega of itself. If a function is big theta, if f is big theta of g, then g is big theta of f. So, I mean, I won't go over all of these, but there they are in the slides if you need a quick reference of all the different relationships that help. The reason why this is quite useful, and you're allowed to use these as facts, they can be proven, and maybe you'll be asked to prove one of them one of these days, but other than when you're asked to prove them, you are allowed just to use them as facts. The reason why it's really nice to have them is because there are times you can write proofs that leverage these relationships to avoid having to do extra work, which can be quite nice. Okay, so there's those relationships. I can also break them down in terms of if you know one thing, what else do you automatically get? So if you know that f is big O of g, well then you know that g is big omega of f. And you also know that f is not little omega of g. So f is not, this is saying f is not greater than, strictly greater than g. Because of course, if something is less than, if a is less than or equal to b, then a is not greater than b. And the same thing is holding here. Similarly, if f is big omega of g, then g is big O of f. And f is not little o of g. Now, if you know that f is big theta of g, that is the two are asymptotically equal, well then you get a whole ton of other information. So you know if they are asymptotically equal that one is not less than or greater than the other. So you immediately eliminate all of the little o and little omega relationships that are possible. You also know if f is big omega of g, that g must be big theta of f, and that f is big O of g, and actually that g is big O of f, and that f is big omega of g, and that g is big omega of f. They basically get all of the big operators of each other, so theta, omega, and O, and they get none of the little operators for each other. And then we have, if we know that f is little o of g, so if f is less than g asymptotically, well then of course f is less than or equal to g asymptotically. If f is less than g, strictly less than, then it can't be equal, so it's not going to be big theta. If f is less than g, then g is big omega, so g is greater than or equal to f. And in fact, if f is less than g, then g is greater than f, so g is little omega of f. We also know that if f is less than g, then g is not less than or equal to f. G is not equal to f. F is not greater than or equal to g, and f is not greater than g. So you can see all of those sort of fall right out of the basic relationships. And that's why I said earlier, if you begin to sort of remember our asymptotic operators in terms of their relationship with the regular inequalities, you can derive these from scratch. If you remember that when a is less than or equal to b, that b is greater than or equal to a, if you know that, then, and you know that this would be big O and this would be big omega, then you can derive these relationships as you need them. And there are cases where it's easier to prove one of them than the others, so you can use these equivalent conditions as a way of saving some work. Okay, and then finally we have the equivalent situation for big omega, which is just the flipped version of everything we have up here. And then, just in case you didn't already have enough exercises to do, here are some more exercises, including, I don't want to say which one I think is like this, but including one or two that are challenge exercises if you really have a lot of free time on your hands or you need a character building exercise. And after all of that, we now have enough. We've seen that if we analyze our algorithms on our hypothetical architecture, being mindful that our hypothetical architecture does have enough functionality that it does duplicate the operations that we would need on a typical real architecture. So, I mean, it can do assignment statements, it can do loops, it has memory, it has control flow. And if we count operations on that architecture, we end up with this very synthetic expression. But if we're talking about comparing algorithms based on a big theta expression or a big O expression where all the constants go away, it doesn't matter that much that my algorithm required 3n plus 3 operations versus 3n plus 7 operations, or even 3000n plus 7 operations, because all three of these are big theta of n. And that means not only that we can go forward performing analysis using our hypothetical architecture, but even better, we can actually avoid a lot of that as well. We don't necessarily have to nickel and dime every single operation. We don't have to count the exact number of assignment statements. We just have to make sure that we account for every different part of our algorithm, because what we care about is just this rate of growth. And that means that starting in the next lecture, we can begin pushing forward and analyzing some new interesting algorithms.